Let's start talking about uncertainty in measurements. Now, before we get into the uncertainty part, we do briefly need to discuss measurements. We'll get more into measurements later on, but we do need to recognize that with measurements not only a number, but they also have a unit associated with those. So these are some SI base units, and these are fairly common. So you see length is meter, symbol for that is a small m. Mass, the SI unit for mass is kilograms, symbol is kg. Time is seconds, S. Temperature is Kelvin with K. Amount of substance is going to be mole, we represent that by MOL. And the last two, electric current and luminescence intensity. Electric current will be important later on in chemistry. That's going to be the ampere with capital A. Luminous intensity, candela, don't really use that as much anymore. So now, with measurements, it's typically going to be a quantitative observation, but without units, that number is going to be meaningless. So another thing we have to look at when dealing with measurements is we have to look at something called prefix multipliers. All right, you're going to need to know all of these from femto to tera. Now with prefix multipliers, this is going to be an easy way to represent numbers using units rather than writing out these long numbers. For example, if I look at having 1 terameter, I'd write that as 1 capital T small m, because the symbol for tera is capital T. 1 terameter would be equal to 1 trillion meters. So then, rather than writing out all of those zeros, we can just write 1 capital T sub m to represent the 1 trillion meters. And we can do that the same with the rest of them. Now, I'm just using meter as an example here. We can use grams, we can use liters, we can use a lot of different other units in place of this. Now, the other thing we always want to be doing is we always want to write our values in proper scientific notation. So, for example, our 1 terameter again, 1 capital T sub m, would be equal to 1 trillion meters, or the way we could represent that is 1 times 10 to the 12th meters. And if you notice here, we've got 10 raised to the power of the number of zeros. As you look at the rest of these, just remember, as far as scientific notation goes, you always want to try to use scientific notation to represent values. And as we go to fewer and fewer decimal places, the value turns to a negative number. So if we look at, for example, 1 decimeter, that would be equal to 0.1 meters, which is 1 times 10 to the negative 1. We move the decimal place to the left 1 spot. Okay, if we look at 1 nanometer, 1 nanometer is 0.000000001. We move the decimal place to the left 9 places, and that would be represented by 1 times 10 to the negative 9th. So you need to be able to recognize these symbols and the values, both in terms of what's listed here as their multiplier as well as the scientific notation. Remember, you need to know tera to femto. And keep in mind that these prefixes can apply to any of these base units. One thing to note is that even though the SI base unit for mass is kilograms, we would use grams for the mass unit with the other prefixes. All right. So let's talk about something called derived units. So we're going to take some of these base units and create new units from them. So for example, volume is a derived unit from length measurement. If we look at a cube is going to have a length, a width, and a height, all of which are going to be length measurements. When we multiply length times width times height, we get the volume of a cube. So let's look at the yellow cube in the lower right here. Has a length, a width, and a height of 1 centimeter. So the volume of that cube would be 1 centimeter cubed, 1 centimeter raised to the 3rd power. Now this is going to be an important factor because we use this as a basis for a more common unit of volume, which is milliliter. So 1 centimeter cubed is equal to 1 milliliter. You need to know that conversion. Now if we look at a cube that is 10 centimeters by 10 centimeters by 10 centimeters, we would get 1,000 centimeters cubed, 10 times 10 times 10. The volume for which would be equal to 1,000 milliliters. Remember, 1 centimeter cubed is equal to 1 milliliter, so 1,000 centimeters cubed would be equal to 1,000 milliliters. Or we could represent that as 1 liter. So this is how we're getting our volume units, and this is how volume relates to those base units. So it's a derived unit. Now, typically with liquids, we think strictly in terms of a volume measurement like milliliters. So a more appropriate way of measuring liquid volume is using glassware like these, such as a graduated cylinder. We have a volumetric pipette. We have a burette. We have a volumetric flask. All of these are different ways of measuring volume of a liquid. However, we wouldn't be able to use them to measure volume of a solid. Now, another derived unit is something called density. If we take the mass of a material divided by its volume, we get its density. Now, different materials are going to have different densities, which can help us explain certain properties. So if we look at, for example, at the density of oxygen, it's 0.00133 grams per centimeters cubed. So it's going to be a very, very low density. If we look at ethanol, which is a liquid, it's got 0.789 grams per centimeters cubed. So it's heavier. So if we put liquid ethanol and oxygen together, the oxygen is going to float. The ethanol is going to go to the bottom of the container. Not just because they're different phases, but also because of their densities. If we look at liquid ethanol, which is 0.789 grams per centimeters cubed, versus, let's say, aluminum, which is 2.7 grams per centimeters cubed, obviously the aluminum is more dense, so if we put aluminum in ethanol, liquid ethanol, the aluminum will sink. The more dense the material, the heavier it'll be per same volume, and it will sink. All right, so density is another derived unit coming from mass and volume. Now, temperature is another common measurement that we need to talk about, and we're going to have 3 different scales with 3 different unit labels for temperature. So you can see the different scales are Fahrenheit, Celsius, Kelvin. Now, with Fahrenheit, Celsius, and Kelvin, we're going to have different units for those. For Fahrenheit, we'll have degree Fahrenheit. For Celsius, we'll have degree Celsius. For Kelvin, we'll just have Kelvin. It doesn't have a degree associated with it. So now, in looking at these scales, we can see that they have the same properties listed, but different numerical values. For example, if we look at where water boils, on the Fahrenheit scale, it's 212 degrees Fahrenheit. Celsius, it's 100 degrees Celsius. On the Kelvin, it's 373 Kelvin. So this goes to show the importance of units. All 3 numerical values are describing the same physical property of water, basically its boiling point, but all the numbers are different, and they'd be meaningless without the appropriate unit. This is going to be similar to the way that a mass of an object has different values, whether you're using pounds or grams. Now, we're going to look at some relationships between these different temperature units and look at ways to convert between them. First of which, we're going to see here Kelvin is going to be equal to whatever our degree Celsius is plus 273.15. Our degrees Fahrenheit is going to be equal to 9/5 our degree Celsius plus 32. We can use these equations to convert between the different temperature scales. You need to know these equations, and you need to be able to carry out these conversions using these equations. But it's a fairly straightforward process. You need to know these equations, and you need to be able to carry out these conversions, because it's going to be very important to be able to convert between these different temperature scales.